In this video, you'll be learning about the heat of combustion and how to solve problems on heat of combustion. But before then, I am Charles the Science Chef, creator of the Science Chef Academy YouTube channel, your online STEM study room where you can learn, grow, and succeed in any of your science, technology, engineering, and mathematics subjects. Heat of combustion, also called the enthalpy of combustion and represented as Hc, is the amount of heat released when a substance burns completely in oxygen. When 1 mole of the substance burns completely in oxygen under standard conditions of 25 degrees Celsius or 298 Kelvin and 1 atm pressure, it is said to be the standard heat of combustion, Hc theta. It is measured in kilojoules per mole, though it can at times be measured in kilojoules per gram. Combustion is an exothermic process. This implies that the value of the heat of combustion of any substance is always negative, and the higher the negative value, the higher the amount of heat liberated by the given mass or mole of the substance. To calculate the standard heat of combustion of a substance, we apply the formula H equals to minus Q over N, where Q is the amount of heat released by the substance when it burns in oxygen, and N is the number of moles of the substance obtained by dividing its mass by its molar mass, and the negative sign shows its exothermic value. To evaluate Q, we commonly use the principle of heat transfer, which is the heat released by a substance equals to the heat gained by, say, water, and that heat should be able to raise the temperature of the water by at least 1 degree Celsius or bring about a change in the state of the water. Mathematically, we can represent this as Q equals to mW times Cw times change in T, where mW is the mass of water, Cw is the specific heat capacity of water, and change in T is the change in temperature calculated as T2 minus T1. Let's now see how to apply this formula in solving problems on heat of combustion. Example 1. 0.19 grams of methanol is burned and the heat energy given out increased the temperature of 100 grams of water from 22 degrees Celsius to 32 degrees Celsius. Calculate the enthalpy of combustion of methanol, given that the specific heat capacity of water is 4.184 joules per gram per degree Celsius. In this question, the substance undergoing combustion is methanol. We are given the mass of methanol, the mass of water, the specific capacity of water, and the initial and final temperatures, and asked to calculate the enthalpy of combustion. So, using Q equals to mW times Cw times change in theta, and substituting the values to be 100 grams times 4.184 joules per gram per degree Celsius times 10 degrees Celsius. So this and this will go. We'll obtain 4,184 joules as the heat released by the methanol, which was used to raise the temperature of the water. From mass over molar mass, we'll calculate the number of moles of methanol. Therefore, the enthalpy of combustion of methanol, HC methanol, will be calculated as minus Q all over what? N. Minus Q released by methanol all over number of moles of methanol. So that will be minus 4184 joules all over 0.00594 mole. That gives us minus 704,377.10 joules per mole, which is the same thing as minus 704.38 kilojoules per mole. Example 2. 0.22 grams of propane was used to heat 200 cm³ of water at 20 degrees Celsius. Calculate the final temperature of the water, given that the standard enthalpy of combustion of propane is minus 2220.1 kilojoules per mole. Take the specific capacity of water as 4.84 joules per gram per degree Celsius. This question is a bit different from question 1 in the sense that we are given the volume of water in centimeters cube instead of its mass in grams. So to get the mass of water from its volume, we use the conversion 1 gram of water equals to 1 cm³ of water. This is because the density of water, raw water, is 1 gram per cm³. Also, unlike question 1 where we are asked to calculate the enthalpy of combustion, here we are asked to calculate the final temperature of the water. Therefore, the first thing to do is to find the value of Q, that is the heat that was released from the propane gas burned in oxygen, using H theta combustion equals to minus Q all over N. So that Q here will be equal to minus H theta C times number of moles. To substitute, you have minus into minus 2220.1 kilojoules per mole times number of moles calculated as mass over molar mass, and the mass of propane given to us is 0.22, while the molar mass of propane is 44. So this is 0.22 grams over 44 grams per mole. If we evaluate this, we'll obtain 11.1005 kilojoules, which is 11,100.5 joules. 11,100.5 joules as the value of Q. That's the value of the heat that was released by the propane when it burned in what? Oxygen. And I'm going to apply this value in the formula Q equals to MW times CW times changing what? Theta. That is, we go back here, our volume of water is 200 cm³. So if 1 gram of water is equal to 1 cm³ of water, it means that our mass of water here, mass of water will be 200 grams. Okay, so coming back here, we substitute that here. That will be 200 grams times 4.184 joules per gram per degree Celsius times, what's the T1? Our T1 is 20. Now we're looking for T2. That's T2 minus 20 degrees Celsius. Okay, this is 1100.5 joules. So from here, our T2, so for T2 minus 20 degrees Celsius will be equal to 11,100.5 joules all over 200 grams times 4.184 joules per gram per degrees Celsius. This and this will go, this and this will go. Fine. Okay, so we'll be left with, this will give us 13.27 degrees Celsius. So our T2 will now be equal to 13.27 degrees Celsius plus 20 degrees Celsius. That gives us 33.27 degrees Celsius. That gives us the final temperature of the water as required in the question. Example 3. 0.01 mole of methane was burned, and the energy given out raised the temperature of 200 cm³ of water from 18 degrees Celsius to 28.6 degrees Celsius. Calculate the enthalpy of combustion of methane. Take the specific heat capacity of water as 4.84 joules per gram per degrees Celsius. From this question, we are given the number of moles of methane, the substance undergoing combustion, the volume of water, which is equivalent to the mass of the water, the specific capacity of water, and the temperature change of the water, and asked to calculate the enthalpy of combustion. So we'll first find the value of the heat used for raising the temperature of the water by applying Q equals to mass of water times specific capacity of water times change in temperature, and substituting the values will be 200 grams times 4.184 joules per gram per degree Celsius times 10.6 degrees Celsius. So this and this will go cancel out this, giving us 8870.08 joules. Then using HC equals to minus Q all over N, we'll substitute the value of Q, that's 8870.08 joules all over the number of moles. Here you don't need to calculate the number of moles because it's already given to us, so just substitute it directly into the equation or into the formula. So that gives us minus 8870.08 joules per mole, which is approximately minus 887.01 kilojoules per mole. Remember, your enthalpy of combustion must always be what? Negative. So don't forget that. It's now your turn. So if this video was helpful to you, drop a comment and hit the like button. Also, if this is your first time here, subscribe to our channel and turn on your notification bell to always stay updated with our new uploads. Always strive to be a better version of yourself until I see you when I'll see you.